Okay, today we have a problem. It says here, rank the following different combinations of M and R on the basis of the angular speed of the merry-go-round after the sandbag sticks to the merry-go-round. So basically, a merry-go-round of radius R is shown in this figure, is rotating with a constant angular speed. The friction in its bearings is so small that it can be ignored. A sandbag of mass M is dropped onto the merry-go-round at a position of smaller lowercase r. The sandbag does not slip upon contact with the merry-go-round. So they give us all these choices and we have to rank them as to the basis of angular speed. So combinations of mass and different lowercase r's. So the sandbag is basically dropped at various r's along the merry-go-round. They want to know the angular speed of each of these different combinations. And so the problem has to be looked at from a perspective, well, what is angular speed? And so we have angular speed is given by omega, which is a funny looking W, but it's omega, and that is the number of rotations in a unit time. And you can see the dimensions of this being RPM, and you can see another dimension would be radians per second. Okay, so what is omega? Well, another definition is this. By definition, it's a change in an angle over change in time. And so this could be considered 2 pi radians over the period. And I give a large case T here. So this would be the period. All right. Because what we're saying here is one rotation equals 2 pi radians or radiuses, and if you do that, that's in one period. So that's where the T comes from. So radians is a unit that is dimensionless, and we say one rotation and per unit time would be the period, and that's the time it takes for one rotation. So it's 2 pi radians over the period. Okay, so it's interesting to note here that since all parts of a rigid merry-go-round rotate about the same axis of rotation in the same amount of time, thus all parts have the same rate of rotation, or the same number of rotations over a unit time. So positions further out on the merry-go-round would travel a longer path, of course, than positions closer in, but and so they have a greater speed. That's not to be frowned upon, but that's not what they're looking for. That's a linear speed then. You would be talking about a linear speed here. But we're talking about an angular speed, and we're sweeping the same angle out per unit time. And that's the trick to this problem. And so since all the parts of the rigid body merry-go-round are sweeping out the same angle, so the change in angle over the change in time equals the same. And that means the angular speed is the same no matter if you drop the masses, any mass of any value, and on the merry-go-round at any radius. So the answer here would be rank from largest to smallest. If the items are equivalent, overlap them. So you would take all these into the field where the answer goes, and you would just overlap all of them. So you'd have a whole bunch of these just sitting on top of each other, and that would be the answer to this problem.